All right, so this is going to be a bit of a critical look at this paper that's come out. I've seen people calling it the Hendon paper. Properly, it is called Mendez Harper et al., and it appears in Matter. And this is the paper that people have been talking about with respect to adding water to grinding for coffee. Lance Hedrick's made a video on this, Papa James, Sweet James, isn't he beautiful? He's made a video about this, and so it's become fairly popular. It's gotten a lot of publicity, and so I thought, if there's anything I can add, it's that with my background, having published research before, I'm going to look through the paper and kind of point out some of my thoughts about where I feel like people need to be careful in their interpretation of the results of this paper. And I'm also going to be looking at another paper that these authors have put out, also kind of concurrently, that does change, I think, some of the overall conclusions that you should take away from this, because I think with the publicity, there's been a lot of talk about static and its effects on coffee and espresso extraction. And I don't want people to get too carried away, because I think maybe some things are being overstated, right? And so that's why I want to just kind of walk through this paper with you and show you kind of what it says and some of my thoughts along the way and some of my conclusions and questions coming from this research. And before I go on, I will be doing some testing later, and so the first of this may be really dry because it's a reading of a scientific journal, all right, a scientific paper. So if you want to skip past what you may find to be rather dull and skip on to the testing and actually see, whether I can replicate what they did at all, I'll put some timestamps into the description of this video, or if you mouse over the time bar, or if you mouse over the progress bar on the video, you can jump straight to those tests, right? Don't bore yourself to death, because this may be a little dry as we go along. So one of the first things I want to point out is, even though this is kind of a critical look at the paper, it's not going to be an adversarial look. I'm not trying to start an argument. It's just whenever you're doing science, you do want to be very careful about what you're saying, what you're not saying, what the data supports, what your experiments are able to speak to, and things like that. So that's really what I'm going to be focused on in this paper. So just to start off here, triboelectrification, right? And you will see these two words, and look, it makes me cringe. People using overly specific scientific lingo in normal conversation. So triboelectrification is simply friction static, right? Static charge from friction. The other type of charge that they talk about in this paper is fractoelectrification, which is static from fracturing processes. So I'm just going to talk about friction static and fracture static, and probably not that much, because really it's just static, and who really cares where it comes from? Well, in-depth science stuff, but really for this paper, it's not really a huge deal for our discussion as it applies to making espresso. So all that to say, if you use the words tribo or fractoelectrification in a normal conversation on Reddit, or in a forum, or in a discussion on YouTube, you're overselling it a little. That's all I'm going to say. So again, why this is important is in this discussion about static, look, a lot of people are getting carried away, I think, and they're looking at ways to mitigate static because of what they're seeing coming out of this paper. But what if static isn't actually the problem? Their main test when it concerns extraction and making espresso is that they add water to the grinding and then see some changes. Well, adding water is not simply controlling static. It could do some other things. They call that adding extrinsic water, right? And so this is a big point, is that they're adding water to the grinding. And so some of my questions revolve around, is it really static that we should be concerned about? Or is there something about adding water itself that changes things? So let's just walk through the paper and I'll talk about it as we go. We start off in their abstract. During coffee grinding, coffee particles turbocharge, causing particle aggregation. So then they go on to say these aggregates pose challenges for preparing reproducibly tasty espresso. Now this is a claim, all right? do those aggregates actually pose challenges requires some evidence. And some of my initial questions when I read this is, okay, static does cause particles to aggregate. I don't really doubt that, right? Static's going to cause some things to stick together. But one big question is that the same as a particulate that is larger due to being just a larger randomly ground particle? Because if static causes two smaller particles to stick together and then measure as a larger particle, that could be different from an actual physically larger particle that is just one particle. And so it's not obvious that just creating aggregates actually changes anything, right? Because it's just static cling, and that tends to not be a real strong force. And, whenever we're preparing espresso, we smash everything together under quite a bit of pressure, right? Just whenever we're, tamping the puck, there's a lot of pressure involved. So it's not obvious to me that just the particle aggregation from static would actually pose a challenge for preparing espresso. Okay, and then they make another claim here. Through the control of the humidity and adding extrinsic water, we demonstrate control over the extent of turbocharging, resulting in increased mass extraction and posit opportunities to improve coffee preparation reproducibility. Now, here is, again, another claim that they can control this turbocharging, and that results in increased mass extraction. So, again, this is one of my questions here, is this kind of implies two separate links. Number one, that water can control static, and number two, that static affects extraction, right? So in that linked process, my questions revolve around what about some direct links between water and extraction itself, where static doesn't matter. So as we read through this, that's kind of my initial questions about the paper. Is there some omitted variable that could be related between H2 and extraction, and the whole static angle may be going in the wrong direction? So now into the proper paper itself, and this is why I said people are referring to this as the Hendon paper. However, if you look at all the different co-authors here, there's a lot of people involved. Now, he is the lead author, and so he probably will be the person that you see discussing the paper everywhere. However, in academic literature, it's always alphabetical, and thus this paper, when it's cited, will actually be called Mendez-Harper et al., right? And that is the official citation for this paper. So then they say, at the brewing level, aggregation may also affect liquid-solid accessibility, leading to inhomogeneous extraction and unpredictably unpleasant espresso. Now, the citations here don't specifically talk about static aggregation. They link to a book and some other papers on a simulation result about modeling the particle size distributions and how that may affect flow rates. So I would say that these don't necessarily support that static aggregation actually matters. Aggregation does, but most of the aggregation being discussed, I believe, in these citations. I don't have access to the book. It's Scott Rao's book on the physics of coffee extraction. I think they're mostly concerned with particles, where the particles are thought to be solid particles rather than aggregate particles caused by static. And again, fundamentally, I do question whether particles sticking together due to static electricity can really have that large of an influence. And so even though there's some citations here, that doesn't necessarily mean that that is supportive of the static caused result. And so, again, my main questions here are all aggregates the same? Is physical particle size versus an aggregate caused by static really going to have the same consequence on extraction? I wouldn't think so. And so that's what I'm looking to see some data for that in this paper. So I'm going to skip to figure 1 now. So this is on the 3rd page of the paper, and they do some interesting stuff. And so they actually do a test with various materials to see how the material interfaces with coffee to produce static. And what they find is that, glass or plastics tend to result in high static charges, whereas metallic surfaces really don't generate nearly as much static charge. And so this could be important to the manufacture of grinders. Typically, what I would say this result kind of says, the less interaction with non-conductive materials, probably the better if you worry about static charge. So if you have all metal paths that are all grounded really well in your grinder, you're probably going to end up with less static. Now, static where it results in particles blowing all over the place on your grinder is from uniform charge, because what you need is a bunch of things of the same charge to push away from each other. And that's where you get these particles flying around. If you've got particles of both positive and negative charges, they will actually tend to stick together. And so what you really are looking at are these high uniform charges that create particles that blow all over the place and create a mess. And what's interesting about that is that that actually should result both in more overall static charge, but also less of this aggregation, because if everything is positive or everything is negatively charged, you would not really think that you'd get aggregates that much. However, they also show that most of the charge is not uniformly distributed in the size of the particle, and so bigger particles don't have as strong a charge as weaker particles do. So you tend to get stronger charges in these smaller particles compared to the bigger ones. So figure 1, really interesting, just in kind of showing in this panel B that the material of the grinder may have a big impact on the amount of charge that you see. And so if people are out there trying to replicate this result, that may have a big impact. If you've got a grinder with an all metal pathway, you may not see big influences from static because, well, you may have less static to deal with to begin with. If you've got a grinder with a lot of plastic in the path, then you may end up with a little bit more static to have to deal with. So next up, they do a lot of tests with a lot of different varieties of coffee. And so in figure 2, they've got a bunch of different results where they show how different types and different roast levels of coffee result in different charge types. So whether something ends up being more positively charged or negatively charged or not charged at all. And so to me, what I really looked at was in panel B here, you can see that as the roast level decreases, and so higher agtron values are going to be lighter roasted coffees, you tend to get more positive charge in here. But right around an agtron level of like 80 to 85, you get almost zero net charge. Now, this is a fairly light roasted coffee. This is like a city roast. But those coffees should have less static and may just exhibit less problems overall if static ends up being what matters. Now, darker roasted coffees end up being more negatively charged, and they're going to have more static in general because just a higher overall charge level, negative, but that basically just means negative charge in this chart. The other thing was on the water content, right around 2.5%. Water content in the coffee. Now, this was pre-ground water content, seems to have basically no charge. Whereas, again, as you get drier coffee, you tend to get larger negatively charged coffee. Although they also show that at very high water content, you start to get positive charge levels, which was kind of weird. They had some hypotheses about that, but again, water content does seem to matter, and that does make sense. Overall, the trend was higher water content led to less charge. Lighter roasts tend to have less charge. So now I'm on to page 6, and in this first paragraph, they do say some interesting things. One of the things is this last sentence here. For now, we can summarize that dark roast coffees appear to charge more negatively, so that is in their result. They charge more negatively than light roasts. That large particles carry negative charges. Again, that's something they show in their particle size distributions, and that commercially roasted coffees charge in seemingly unpredictable ways. Now, this is interesting because when it comes to replicating their results, this means that it may be actually kind of difficult because commercially roasted coffees don't seem to behave consistently. And so, if you're looking to try to replicate what they're doing, this may have some different consequences, because if you go grab a bag of coffee from your local roaster, this is basically saying that they can't necessarily predict how that roast level will correlate to the generation of static in the grinding process. And so all I would say is, again, you got to be a little careful extrapolating the results of this paper to your process, because there's a lot of inconsistency and some unpredictability in commercially roasted coffee versus they actually controlled their own roasting in their process later to really isolate how the roast level affects the generation of static. And so here we get to their standardized roast test, this figure 3, the effect on roast profile on charging. And again, we're talking about static here. And so basically what they show here is, look, the more you roast, the darker the color is in general, but they also show that you end up getting negatively charged coffee whenever you increase the roast time. And they did this on a few different types of coffee. And so that's, all to say darker roasted coffee you would tend to think would have more static. Now, this panel C and panel B are almost the same thing flipped, because this is Agtron color, which is going to be strongly correlated with roast time. And so this is basically saying darker roasted coffees have stronger negative charges. Lighter roasted coffees tend to exhibit less charge, less static. And this also corresponds to water content, where the more you roast the coffee, the drier it gets, the more negative the charge, right? So that all seems to make sense that, yes, water does tend to affect the strength of static in coffees. Now, what you probably want to take away from this is, as far as static goes, darker roasted coffees you would think are probably going to end up drier, and they are probably going to end up exhibiting a bit more static during the grinding process. All right, so on page 9, they say something that I'm not really certain about from my experience. It says, look, in this figure 4, it offers one explanation as to why darker coffees may yield slower espresso shots for the same brew parameters. That is not what I have ever experienced. To me, darker roasted coffees tend to always run faster, in my experience. Now, again, who knows, but they're saying the opposite happens, and I don't know what your experience has been with that, but I've searched a little on the internet. It seems a lot of people don't have this experience. A lot of people have the experience that darker coffees tend to run faster. So, they're saying that darker coffees may generate smaller particles and so may run slower, but I don't know. Again, to me, darker roasted coffee, I always tend to have to grind it finer to get it to run slow. So, I don't know. Let me know what you think about that. Okay, I'm going to rant a little bit, because here it says, adding moisture. And so we're going to get into the heart of what everybody's been talking about. And this says, known in the coffee industry as the Ross Droplet Technique. All right, now listen, I'm never going to call it that. And the reason is nobody named Ross invented this. Adding water to things to reduce static is not some new novel invention. And nobody, again, named Ross came up with this. Now, I'm just saying, look, when I was a kid, Mama used to run the comb through water because it would keep my hair from sticking up from static, all right? Adding static to things to reduce electricity, is even in the grinding process, adding water to reduce static is common old knowledge. So here we are on the Encyclopedia Britannica, and it says, in the 1400s, Smiths learned to combine the ingredients of gunpowder in water and grind them together as a slurry. This was a significant improvement in several respects. Wet incorporation was more complete and uniform than dry mixing. The process froze the components permanently into stable grain metrics, blah, blah, blah. And wet slurries could be ground in large quantities with little danger of explosion. Why? Well, because whenever you grind something dry, the particles tend to float in the air, and that airborne powder mixture, if you ever had static go off, would get ignited much easier than if it was contained in a wet slurry. Here's a document from Congress from 1995, Technology and Policy for Suppressing Grain Dust Explosions in Storage Facilities. And here it says, look, in 1982, the USDA Grain Marketing Research Laboratory completed a study that had been requested, blah, blah, blah. The study found that additives applied properly and at correct locations can reduce fugitive grain dust. So it reduces the dusting. This is going to be, by the way, important for our later discussion of this paper. Water addition at the leg dramatically reduce the fine dust particles, increase the moisture content, lessening the electrostatic activity within their leg, reducing ignition source volatility. So again, this is old knowledge. Adding water to dust reduces its dustiness and reduces the static, right? Reducing the static and grinding, reducing explosion characteristics and ignition characteristics. Again, this is not something that is new, nor was it invented for coffee. So to drive this just the last thing home, this is a video on primer manufacturer at Federal. And so this is an explosive manufacturing facility. And so again, just listen right here.
Is doing the charging, standing in water on an anti-static mat. He rubs the ball of.
All right, so in this environment, they literally put water all over the floor to mitigate static charge. Because this is explosives and they do not want any detonations in here. And so they don't want any static buildup so that any sparks can occur. And so again, all this to say, again, adding water to a grinding process, adding water to reduce static is old knowledge. And so, yeah, I'm not going to be calling it anybody's technique. It's just adding water. All right. So I'm sorry. I had to rant there a little bit because I've seen this for a while now. But you don't get your name on something because you took ancient knowledge and applied it. Sorry, I'm not going to do that. So now with this, we get to figure 6a, which is kind of the main payoff of, look, when you add water to the grinding process, yeah, static charge is reduced, right? And so this is what they show across all different kinds of coffee. You see this trend for negatively charged coffees to be reduced in charge, positively charged coffees to be reduced in charge toward 0 on this line. They also show that it changes the particle distribution here. And so you see the large particles got reduced as they added more water. The distributions kind of moved the peak over to a smaller, and there was less of this kind of long tail of large particles. And so basically what they think is happening is that fewer aggregates are being formed, that the big particles that are, a big particle with a bunch of little ones stuck to it that makes a larger overall particle is being reduced because now you're getting more free-floating particles and less aggregates. And so you get your distribution shifted from these big aggregates to smaller uniform particles. That's kind of what they're saying is happening. And again, obviously static charge is being reduced. That is clear in their data. Now, the thing that I want to talk about here is this aggregate, right? That they're talking about going away. That these aggregates measure as larger particles. So let's talk about how particles are measured. How are particle sizes measured in Espresso? So this is one of the instruments that they use to measure particle size. It's a Mastersizer 2000. It is a laser diffraction system. And the other method that they used was a Keyence digital microscope. And so both of these are optical systems to recognize particle size and to categorize particles. And the only reason that I mention that is just to go back to that point that whenever you talk about particle size, there are different things that you can mean about that. So just as a visual illustration, right, if I've got two particles here, clearly one is bigger than the other. And if these are solid particles, that's pretty clear about what that means. However, if you have something like this, which ends up being an aggregate particle versus a smaller particle, this one optically may still measure as a larger particle, because when they take the measurement optically, all of these particles look like one because they just block the light. And that's how these things basically are going to work. And so with that, that's where one of my questions are: all particle sizes the same, right? Meaning, is a big solid particle the same as one of these aggregates when it comes to affecting extraction? And I would say that I would assume that they would be different. Just because you get a larger particle as an aggregate, to me, does not mean that that's going to have the same impact as something that is actually physically one larger particle, especially when it comes to availability for extraction and things like that. Water might be able to get in between these particles much easier than it can get internal to this one large particle. So that's one thing whenever you talk about the particle size distribution that I do have questions about, because I don't know enough about this. It's not my field. But the way these optical systems work, I don't believe it can distinguish between aggregates and solid particles. But I do think that those might matter for extraction purposes. Now, one of the other things I'll point out is that to get to like a zero charge level, the amount of water that's being added is 10 to 15 microliters per gram. And so if you're not aware, 100 microliters is a milliliter and 1 milliliter is 1 gram. And so whenever you start talking about the amount of water that you need to add to a shot, it's actually quite a bit. If you're looking at an 18-gram dose, you're looking at about 0.2 grams of water to add to that thing to mitigate your charge potential. And whenever you look at their tests, they added quite a bit of water in their tests. So to fully nix the charge, what they found is you do have to add quite a bit of water in order to make that happen. Now, at the upper end, this 20 microliters per gram, that's getting close to, it's basically 0.36 grams of water to add to a 18-gram dose of espresso beans. So pretty heavy there. All right, so here on page 12, we get to figure 7, which is one of the big main results that everybody's going to focus on with this paper, right? Where they test and find that adding water to shots increases extraction and increases shot times. So shots ran a lot slower and achieved higher extraction. Now, these are very large quantitative results because it's about a 50% increase in shot times and roughly a 10% increase in the amount of coffee that was extracted in that process. So these are very, very large effects, and these should be easily replicated results. Like anybody should be able to see these results if it really drives this magnitude, right? I mean, there is no mistaking a shot that goes from taking about 30 seconds to one that takes 45 seconds. That is a massive increase in extraction time. And so this is one of the things that I do plan on testing because even in the quick test that I saw that Lance Hedrick had already done and James Hoffman has already done, you know, this doesn't really show up, not nearly to this magnitude. So I do wonder a little bit if there's something else going on, because this has been difficult to reproduce so far. And so I'm going to find out in my own tests whether I see these results. Now on this, if you want to look at the details down at the bottom of the paper, they go into some of their methodology. And so here you can see that they pulled their shots at 7 bars with 94 degrees C water. They went 18 grams in, 45 grams out. They applied 196 newtons, which that works out to be about 22 kilograms or roughly 44 pounds of force, which is pretty stout, right? I mean, you can't say they weren't tamping that puck enough. They also used a puck screen on top. So if you're wanting to try to replicate it exactly, I think they also used like a kind of a medium to dark roast coffee on this. But again, 18 grams in, 45 grams out for this test. And I think they were doing 20 microliters per gram of water, which would be 0.36 grams of water. On these results, again, they make some statements that I'm not fully on board with. So they say, look, first, the shot time is nearly 50% longer. And then they say, we understand this to be due to the increased bed density because the fines and boulders are not electrostatically attracted to one another. That, to me, is not necessarily supported. Now, it is true that their average particle size is smaller. It is true that they measure lower electrostatic charge. However, just because you see those things in combination does not mean that one is causing the other. This is a very classic correlation versus causation problem. Because again, what they're actually testing is adding water, and then they're looking at shot time and extraction, right? So if you think that this is going through and static is affecting this, the problem is, what about other things, right? So there could be omitted variables here. And so just because you measure static changing because you added water, again, basically what you end up with is it could be due to static, but your test by itself did not distinguish that static is what's causing these differences. And in their other paper, I think they really kind of drive this home that it actually probably isn't the static as much as water might change the particle size that you achieve during grinding. And that could be related to static, but again, it may not have anything to do with the static causing boulders or not, right? The aggregate particle size. That may not be the effect. One of the things they see is that whenever you add water, you also get less retention. And so it could be that you're getting more fines, period, on the output. And so again, that may be because there's less static to have it stick to your grinder, but it might not be because static is causing the average particle size to change. Because again, and I keep saying it, aggregates caused by static may not matter. And again, based on this test, you cannot necessarily conclude that static is what's causing this. Now, water, yeah, you can say that adding water changed this, but again, more than one thing can be happening at the same time. So it might not be static. It could be the water itself doing other things in this process. Now, if you're trying to push and say, okay, but you need to offer some alternate hypothesis, you just can't say, that's not true. Fair enough. So here's some things to think about when it comes to what else could water be doing. And I already mentioned water could be changing retention in the grinder, which is something they find. Water might cause those particles that are very light and might float away and might have enough static charge to cling to be ever so slightly heavier for the same size because of a slightly higher moisture content, so that they would be less likely to be caught by air currents. They would be less likely to be stuck to the side. And so they might be more likely to exit the grinder, and thus you end up with more fines in your output. And again, that would be congruent with their data and not necessarily have anything to do with static aggregation. What about adding water might cause the puck to be slightly better hydrated, and that might increase the wetting factor, which is basically when water contacts a surface, does the surface tension of the water get broken enough to actually seep into that surface? And when you're dealing with pucks, that could be an issue, right? That water, because of the higher hydration, actually finds it easier to enter the puck than if the puck is very, very dry. And you see this sometimes with soil, that extremely dry soil can have difficulty absorbing water. And if you've ever done any gardening, you might encounter this, that sometimes it can be difficult to water soil. It's known as hydrophobic soil. And this happens a lot of times because the organic matter can get a little waxy sometimes. And you'll basically see beads of water sitting on the surface, and they won't just immediately go into the soil. And so sometimes once you finally get it a little bit wet, it can start absorbing more water very rapidly because it just needs a little bit of help getting started. And so, and if you go to Wikipedia, it talks a little about this, that basically this hydrophobic soil is partly because of you can get waxy compounds in soil because the way the organic kind of natural oils and stuff can behave whenever they get dried out. And to me, something similar might happen with coffee. And again, I'm not an expert in this field, so maybe I'm totally off base. But coffee does contain oil, and that oil might become a little waxy when it's dry. And it could be that adding water during grinding hydrates the coffee a little bit and can maybe get through that waxy layer to increase wetting. And so it could be that the flow rates and everything that you're seeing changes, and the extraction changes, and it may have nothing, relatively speaking, again, to do with static. It could actually be this kind of hydrophobic property of extremely dry organic matter. And the last thing that I'll say about an alternative hypothesis to their result, this again is from addendums to their paper. They found that adding water to the grinding process lowered the amount of heat in the coffee. And so typically, the temperature of your coffee, I've found, does change the extraction a little bit. Now, I don't know, this is a bit of a stretch. I'm not saying that this is a strong hypothesis. However, there was quite a big difference in the amount of temperature flux during grinding that when they ground dry coffee, it went from 18 to 30, which is a 12 degrees Celsius increase in temperature. When they went with water, it only increased about 5.5 degrees. And so with that, again, you're looking at twice the temperature rise, and maybe there's some impact of the temperature impact, right? Now, again, to me, that's a pretty weak hypothesis. I'm just, again, offering some alternative explanations of what other variables might one consider, not just running with the static story. And so with that, let's move over to the other paper that they've put out, because this is one that you may not have heard as much about. And this paper, again, is from Joshua Mendez Harper and Christopher Hendon, right? And so this one is called Chemical Strategies to Mitigate Electrostatic Charging During Coffee Grinding. And this paper is really interesting to look at in conjunction with the other, because in this paper, they test other methods to reduce static to see whether they achieve the same results. And so I won't spend as much time in this paper because I know this stuff can be a little dry, but what they actually find is that, again, in this paper, there is some support for a conclusion that it's not really the static that matters as much, because even if you de-electrify and de-static the grounds after grinding, you don't see the big change in shot times or extraction, which means, again, it may not be the static. It could be something else. Now, it could still be the static getting the particles stuck together, and then when you de-ionize them, or de-electrify them, it doesn't undo those aggregates or something. But again, overall in this paper, what they find is adding water changes things in ways that other de-static or de-electrifying methods don't do, right? It changes things in ways these other methods don't. So again, in this paper, it's very directly related to the other. They do the same tests here, and they talk about charges and how coffee gets charged during grinding and the different types of charges that coffee can obtain during the grinding process. And then they go into these charge passivation strategies. And so number one, they test what happens if you just let the coffee sit. And here in figure 2, panel B, you can see that over time, the amount of potential in the coffee decreases towards 0. And what you actually see is, even for dark roasts, which tend to be the most strongly charged coffees with less water content, after, 5 minutes or so, they're pretty much done as far as being statically charged. It does dissipate over time. Now, with lighter roasted coffees, as little as a couple minutes of your ground sitting there can get rid of the static. Now, what else they do? Well, they try static reduction using ion beams, corona discharge, and radioactive static eliminators. So again, they try multiple methods for eliminating the static electricity in ground coffee. Now, all of these, other than the water, are done after the grinding process. And so here in figure 3, panel B, you see the charge reduction using a high voltage ionizer, panel D, charge reduction using a radioactive ionizer, and they're both effective. We see for highly negatively charged coffee that it increases charge back towards 0 as you apply higher levels of ion density, and the same thing goes for other types of coffee that you can, by varying the amount of ion density, get those back to a 0 charge. Then with the radioactive ionizer, you can see vast reductions in static charge. In both of these charts, you can get them back towards 0 with an appropriate radioactive ionizer. So the test here then becomes, if you get rid of static, does it matter how you get rid of static, is basically what they're testing. And so here's some follow-on data that they have, and this is where I think, again, my alternative hypothesis for what's going on kind of start to take shape, because here's some things that you see. The particle distribution of expelled and retained grounds. And you see this dark brown is the coffee that came out of the grinder, and this brown dotted line, that is the coffee that was kept in the grinder. That is retention. And those two brown lines are without water. And you can see that really fine grinds are more likely to be retained than expelled whenever you don't add water. Now, when you added water, you got less retention, and so the overall shape of the profile is in between. And that means whenever you add water, you get less retention. More of the fines leave the grinder and end up in your puck, basically. So you end up with more fines. Now, what's interesting about this is if you think about the alternative hypothesis here, you've got one that says, hey, it's these aggregates because static sticks things together. Maybe, but you can see it also just purely affects the number of fines, period, that comes out. And so it could be less about the electrostatic forces and more about how water just helps get all of the grounds out, because water reduces dusting, right? Like I showed you, and this is where I said, those industrial studies with grain silos and explosives where you add water to reduce the dust, because this is one of the effects. Whenever you have very, very dry ingredients, the really light particles tend to float, and they don't always go where you want them to as easily. Now, static could also be in play, but I'm saying there's more than just static potentially happening here. And so, like I said, that's one important thing. You can also see that if you add too much water, you start to get water-driven aggregation, where things start to stick together because they're damp. And so the water content, there is kind of a sweet spot they find where the particle size is at a minimum. So you kind of eliminate the static, you eliminate the dusting, but you haven't gone so far that you're ending up with like mud or sticky particles coming out. And, you know, here in panel D, you can see the retention using water is just way less. Now, ion treatment doesn't matter because that is done after the coffee leaves the grinder. So yeah, I mean, surely adding water does seem to change some things. Is it static? I'm not convinced. So then we get to their tests, and here again, they're testing, does adding water behave differently than these other static mitigation strategies? And it turns out it does. And so here are the charts. These are from the previous paper, the same things, where you see increased extraction, increased shot time whenever you add water. Now, when you don't add water, but you get rid of static through ionization, you don't see these extreme effects. I would probably say these two are indistinguishable statistically. Now, I'm not saying they're not there. Maybe if you ran a huge sample, you might be able to distinguish these. But based on what I'm seeing here, I would expect that you probably cannot statistically separate the ionized or destaticked coffee from the untreated coffee in panel B, right? There's just no effect here, which means static may not really be explaining what's happening. There is something about adding water that I think probably does change things. Now, again, I've got to do my own test to see, because again, these are still really big effects, and I think if it was this significant, you'd probably hear a lot more people talk about this. I mean, look, people do add water to their espresso, but look, I mean, if you're increasing my goodness, I mean, this treatment is, they're different numbers here than last time, but 1.25%. So let's see, that is, let's see, so we got 905 minus 776 divided by 776. We are increasing extraction 16.5%, guys. That is just, that's gigantic, okay? So if that were really the case, that you were getting an extra 15, 16% extraction, the other paper showed 10, people you'd think people would have spotted this. So again, I gotta replicate this. That's all there is to it. Before I believe this result, I'm gonna have to see it for myself. So right here on the next page, the authors themselves basically say this. Thus, unlike the water drop technique, discharging coffee at the nozzle, which means getting rid of the static post-grind, produces limited changes to the physical characteristics of the grounds used to brew coffee compared to the untreated samples. Now, there's a big hole right here, because what you need to see to back this up is to actually do that distribution graph where you see the particle distributions and show how it changes without water, but by getting rid of static, right? That's what you need for this sentence, because this sentence is not supported, right? They're saying it changes the physical characteristics of the grounds, but that's not what they show. What they show is that there's very slight changes to the way the shot flows, but they don't do any statistical tests, right? What I don't see in this paper is, do these non-water deionizing or destaticking or deelectrifying techniques change the particle distribution that you observe in these optical methods? Because if they don't, then the static isn't necessarily fixing the aggregate problem that they're talking about. But you could really start to distinguish between, is it the water doing something else, or is it the static that's happening? But they do kind of, point out any effect at all between using the ionizer and untreated, right? So it's minimal at best, is basically what they're saying. Now, again, I want to see for the ionizer treatments that particle distribution compared to what happens when you use water, compared to what happens when you use nothing. Because again, all of this is basically hinging on, does static cause these aggregates, and do the aggregates, if they're caused by static, actually matter? But the conclusion of this paper really looks like static by itself isn't enough. It really is more about adding water during the grinding process, and that leads me to believe it may not be the static that much at all. It really is maybe the water doing other stuff. It could, be changing the way the particles are retained in the grinder, and so you might get more fines in your puck. It could change the wetting behavior of the puck. But yeah, I mean, what we directly see is if you don't add water, but you do get rid of the static, not much changes. All right, so here's a hypothesis after thinking through and reading through this second paper. Adding water during grinding is less important for low retention grinders, and probably more important for high retention grinders. And so, what I would expect is for, light roast coffee in a low retention grinder, those have higher moisture content. You're probably not going to see very much difference if you do water during grinding or not. Now, if you're using really dark roast coffee that's pretty dry, and you've got a high retention grinder, adding water might help. Now, the static and using all these ionizers and things, the Acacia ion beam thing, this stuff, based on what I'm seeing, probably doesn't do much, because what they find is doing this process after the fact, after it's already out of the grinder, whatever effect that the water's giving, this isn't really going to change much, right? They basically tested the ion beam. That is what this second paper looks at. And what they find is doing this sort of anti-static post-grind isn't really helping, right? It's not changing much. It really is the water. And so those are kind of my conclusions from reading these papers. I'm not very convinced that the static is that big a deal. I'm not saying it doesn't cause a mess, and I'm not saying it has zero effect, but it really seems to be more the water itself is doing something, and I don't know that they've really clearly identified what it is. All right, so if you've made it this far, congratulations, because I know this is probably a long, dry video. But now let's go test this crap, and let's actually see. Do we see higher extraction? Do we see longer extraction just by adding some water to the espresso during the grinding? And so let's go over to the countertop and see if this stuff holds up. All right, so in order to try to replicate the Hendon test, I did try to follow them as closely as possible. And so I used a pretty fresh bag of coffee. I opened this thing yesterday. It's a medium roast. It's the same stuff I've used in most of my tests. I weighed out 20 grams because my target ended up being 19.5 to get my shot times pretty close to theirs with the amount of coffee they were extracting. What I did was I weighed out 20 grams and then I would grind the dose. And once it finished grinding, I then reweighed it and pulled it back down to 19.5. And I did this within a handful of milligrams to get my dosing extremely accurate, because dosing and weight can have an impact on extraction speed. So once I got my dose, I did apply wire distribution just because that's my habit, and I do that with all my shots. I do find that it helps with consistency. So I did a bit of WDT, which, you know, honestly, I did off camera because it was kind of hard to hold that thing in front of the camera and do it. I then tamped using a spring-loaded tamper to get consistent tamps. And then I pulled the shot using my Bluetooth scale that I built so that I could get shot traces for each shot. I do apologize, everything's kind of gross because I've been running a few tests lately and I haven't really cleaned things carefully in between. Now, after each shot, I then tested for extraction yield using my little R2 extract refractometer. And I repeated this, and so I did 3 shots dry and 3 shots wet. Now, for the wet shots, I weighed out 20 grams of beans, and then prior to grinding, I added 20 microliters per gram, which for a 20-gram shot ends up being about 0.4 grams of water. I did this with a pipette. That's what they did in the paper. They didn't use a sprayer or anything, or a spritzer. And after I added the water, I then gave the beans inside of the dosing cup a really good shake to try to get all of the water distributed all over the beans. Now, once I did this, I did find that there was quite a bit of residue left in the dosing cup. And I mean, it is quite a bit of water, so I did dry that out before I ground the beans, and so I ended up with a dry cup that I ground into, and then once again, I reweighed everything and pulled it back to 19.5 grams for the dosing. And so here is the data, and it doesn't look good for the paper, all right? I could not replicate what they saw in my testing. So the 3 dry shots actually pulled a little slower than the wet shots. Not a ton, but a little over a second faster on average. They also did come out to be a little heavy. Each shot was just a hair more. But again, statistically, yeah, there was a little bit of difference in the shot times, but actually the wet shots ran faster. So that doesn't really correspond to the result in the paper. Now, as far as yield and total dissolved solids, I actually found that the wet shots pulled a little less, but it was not statistically distinguishable. They basically pulled the exact same extraction. And so overall, statistically, as far as shot times and yields, there was really no difference between whether I added water or not. Now, given the large change in shot times in the paper, I don't know what to say, right? I mean, they saw their shots go from about 30 to 32 seconds to like 45 seconds. I saw no change to a negative change. So totally different result. On extraction, they saw big increases in total dissolved solids. I found a very, very slight decrease, which was statistically 0, right? I found no difference at all in the extraction yield of these things. And since I did record the shot traces, here's what it looks like, right? And again, in their paper, they get a nice clean separation. And in my shot traces, they all mostly look the same. I mean, as they should. Now, if you look, the yellow, blue, and green, and here you can see they tend to be on the high side because they did pull just a hair faster, but not much. Now, don't pay attention to the time scale. I do a thing with these shot traces to get them all lined up where I chop off the beginning because it happens to be very, very noisy with my machine because I do pre-infusion. And basically, you get a ton of noise before the shot really starts. So I line them all up at 1 gram. And so basically, this is the 1 gram to 45 gram run. And so I do lose the pre-infusion time. So that's why it looks like these shots are all 5 seconds short. It's because, well, I'm missing 5 seconds pre-infusion. So yeah, I mean, no real difference on these. Again, the dry shots technically ran a little faster, but you know, I don't think there's really a substantial difference there. So I really couldn't replicate their paper, y'all. I tried. I did the best of my ability to match what they did. I didn't find it. And so this goes back to some of my concerns with their paper is that the effects that they show are way too big for me to be comfortable really advocating for it, right? I think maybe they need to look at some things, and it could be different grinders, different beans, different setups, because I'm not showing anything. And in some of the other tests I've seen that people have done, they didn't show the big results either. And so I'm going back to it. It may not be anything to do with static. The water itself may change some things. My setup may have very low static to begin with and pretty low retention to begin with. And in that case, I would not expect water to make that much difference. On systems that have a lot of static and have a lot of retention, maybe it would, but I don't know, man. Their result was huge, and I'm just not seeing it. And so that's, I think, where I'm going to draw this video to a close. I know it was long and dry. I hope that you learned something from it, and if you've got any feedback, as always, feel free to leave it in a comment below. Thanks.